Hello everyone. I am Shobhan De, teaching assistant and research scholar of Electrical Department IIT Bombay. And today the video is on finite element method based software ANSYS Maxwell, where we will learn that how to model a permanent magnet machine in this and particular environment. This is a part of the tutorial class of Advanced Electrical Machines course EE6108 of EE Department of IIT Bombay. Okay, so to start with, we have to now first open ANSYS Electronics Desktop software. Double click on the ANSYS Electronics Desktop icon. You will get this environment, and here one active project will be shown in the under the project manager as project 1. Now, if we expand, there are definitions. So our objective is to model a permanent magnet machines in a 2D environment and to run the model in transient simulator. So we want our result to be varied upon time. So we need the solver as transient. So first we need to verify whether among these options, desktop, view, simulation and automation, desktop is selected. After that, we have to come here as per the mouse pointer shown. We have to click here. We have to click on Maxwell 2D to create a new Maxwell 2D file. If we click here, we can get this kind of window, and here we can see a new simulation file is created, that is Maxwell 2D design 2 magnetostatic, and XY, that means it is a 2D one, and within bracket it is written as magnetostatic, so the solver is magnetostatic. At the start of the simulation, we click on Maxwell 2D, solution type, change it to transient, click OK. So this is our environment. Now we have to first draw a motor. So we'll first draw the stator. For that, we'll use the user defined primitive. First go to draw, click on it, then user defined primitive, then RM expert. Then there are many options are here. We'll use to draw the stator slot core option. Here it is slot core. Other options you should explore. So we are clicking on slot core. This kind of dialog box will come. So here we have to specify dia gap. Dia gap is the bore diameter of a inner rotor machine. So for an inner rotor machine, dia gap specifies to the bore diameter of the stator. So we can write here absolute values, as you can see here, dia gap, dia yoke. It is absolute values are written. These are the units over here. But rather than we'll use here variables so that we can change their values afterwards for as per our need. So at dia gap we'll write capital D, press enter. One new dialog box has come to add a variable D. So the name is D, unit type length, unit millimeter. So we'll specify here what would be our diameter. I am specifying it here at 96 as bore dia. Dia yuck in this case is the stator outer diameter. Our variable is DO. Enter. 160 I am inserting here. Length, as it is a 2D simulation, keep length as 0. We are not doing any skewing, so skew is also 0. Slots means number of slots. The variable is QS. Enter. So there is no unit. The value is 36. We are drawing a 36 slot stator. Slot type, if we expand it, like stretch it like this, we can find here in the description the slot type, there are 1 to 6 various slots can be here. Like slot type can be like 6 types of slot can be drawn using this user defined primitive. So we will use slot type 2. What are other slot types you should explore? HS0, this is the slot opening, width of slot opening. So our variable should be HS0, enter, and our value should be 1 millimeter, that's fine. HS1, that is the uh, height of the tooth tip. So HS0 is the height of the tooth tip, and after that HS1 is the slanting portion of a tooth tip. So I can draw it for you. So if my tooth is like this, so from here this is HS0, and up to this is HS1. Okay, and if a slot looks like this, like for our slot 2, it will be like this. Okay, it will be like this. So this is HS0, then HS1. From here to here, this distance, this is HS2, and other things are, so let me write here, this is HS0, this is HS1, then this one is HS2, and if we talk about width, this width, that is the opening of the slot, is BS0. The next one from here to here, this is BS1, and from here to here, it is BS2, and this one is a half circle. So the radius of the half circle is nothing but this BS2 by 2. Okay, so keeping this in mind, we will now specify HS0 as HS0. HS01 is not for our use. HS01 is for closed slot, where the slot is closed like this. To define the thickness of this closed portion, we need HS0. So we are HS01. So we are doing a open slot machine. So HS01 in our case is 0. So HS1 value is 1. HS2 the value is 14 millimeter. BS0, that is the slot opening, 1 millimeter. BS1 4.7 mm. BS2 is 7 mm. Now all the other things, keep them 0, and finally hit OK. So you can see once the stator is created now, the next thing is we'll go to create the rotor. Before that, we'll rename the stator. Double click on the slot core 1 in name, type stator, hit OK. Similar to the stator, we will again go to draw user defined primitive RMX part. Now to draw the rotor, this time we will use PM core. Here it is PM core. Now dia gap of for the rotor of a inner rotor machine is the diameter of the rotor which is close to the air gap. Therefore, for an inner rotor machine, it is the outer diameter of the rotor. So it is capital D minus 2 times Lg, 2 into Lg, where Lg is the air gap length. Hit enter. Lg is a new dimension, so it is 0.7 mm. We are defining. Dia is the shaft diameter. Okay, for an inner rotor machine, dia of rotor is the shaft diameter, DSH. Define it as 20 mm, that's fine. Length is again 0 as it is 2D. Pole number of pole is capital P, enter. We are modeling a 36 slot 8 pole machine, so pole number is 8, enter. Pole type, so there are many pole types. As you have already seen that slot types were 1 to 6 for that particular um, slot core option, user defined primitive. Here pole is also 1 to 5, so 5 pole variations we can draw using this particular user defined primitive. We will choose pole type 1. What are the others? You should just see or check. Pole embrace is EP, enter. So 0.8. Now pole embrace, what is pole embrace? Okay, it is important thing. We may see what is pole embrace. Suppose this is a rotor. Suppose this is a rotor and I am drawing for a surface magnet machine only one magnet. Suppose this is a magnet and this line to this line, this angle is 360 degree by number of pole. That means one pole pitch. Okay, this is this angle, and the pole, this pole, it covers, suppose, an angle whatever. Suppose this angle is something theta. Okay, this angle is theta. So if this 360 degree by P is alpha, then pole embrace EP equals theta by alpha. Okay, so this is what we have to mention there. This EP is 0.8, that means the pole covers 80% of the pole pitch. Okay, thick magnets, that is the height of the magnet, TPM, enter. For our case 4 mm we are defining. Width magnet is not necessary for this kind of machine, surface mounted machine, where we are already defining the pole embrace. If we just define the thickness of the magnet and the embrace of the pole, it is sufficient to define the magnet. This thickness or the width of the magnet is required for this kind of magnet shape. For the interior shape, the width is required. So this is not required for our purpose. We can put it 0 or whatever. This bridge, rib, all these things are required for interior permanent magnet machines, not for surface one. Lane region is also we are putting as 0. Now an important thing is info core. Info core, if it is 0, it will produce the core, that is the iron of the rotor. If it is 1, it will do the magnets plural, that means all the magnets. If it is 2, it is magnet singular, that means only one magnet. If it is 100, it will create the region. So we'll draw the core first. So info core is 0, hit OK. See, the iron is created. Now rename PM core 1 as rotor, hit OK. Copy rotor, select rotor, Control C, model, Control V. So you could see rotor 1, expand rotor 1, double click on create user defined primitive. Do not change anything, just change info core to the value of info core to 2. Write 2 here. That means one magnet will be created. Why it is one magnet we are creating? That I will explain later. Hit OK. See, one magnet has come. Okay. Now let us change this rotor 1 to PM, permanent magnet. Okay. Now let us assign the materials, select rotor and stator. That means the cores. Now there is property window. If you can't see property window in your desktop here, just go to view and see the property. This properties, it is checked. If it is ticked or checked, that means property window will be there. If it is not, check it so that property you can see the property window. Okay. So select rotor and stator, go to material, click on here. So scroll up, there will be edit, click on edit. It will take some time to open the all material library. Before searching for materials, make sure that show project definitions and select all libraries. Both of them are checked. Okay. After that, in the search bar, search as M250. Okay. Now select M250 35A 50 Hz. M250 is the material. It is the silicon steel. 35 mm is 0.35 mm lamination thickness. Click here. Then go to view or edit materials. Okay. Now you can see there is, yes, composition is solid. Make it lamination because this is a this will be laminated, and stacking factor is 0.95. It is fine. Stacking direction, it should be V3. Why V3? I will tell you. Hit OK. Yes. OK. So you can see under cogent power 250, M250, there is rotor and stator. Now why we have done V3? See here, V1 means along X, V2 means along Y, V3 means along Z. Now this is a 2D simulation, so the stacking will be along the Z axis. So therefore the lamination will be along the Z axis. That's why we have assigned it as laminated and the direction is along V3, that is Z axis. So for PM, select on PM, material, edit. Okay. So we will search here N42, that is NdFeB, neodymium magnet 42. We'll select Arnold magnetics, maybe, okay, 100 degree Arnold magnetics N42, 100 degree. Click here. Okay. Now we have to assign that which direction the magnet should flow flux. That means which is the north pole, which is the north side of this particular permanent magnet. Now to define that, we have to first understand how to do it or how the software could understand what is the direction. For that, click on the PM. Again, go to material, click on edit. See the Arnold magnet is whatever we have selected previously, that is already selected. Click on view or edit material. Now you can see here there are X component, Y component, Z component. Okay, to determine the direction. Now X component unit vector is 1, Y and Z are 0. Therefore, the direction would be the positive x-axis direction. Now, of what coordinate? Now, whichever coordinate we will assign to that particular magnet, the x-axis of that particular coordinate will define the north pole of that particular magnet. Okay. So, if it is so, just cancel it. Now, we have to define a new coordinate system to it, of which the x-axis would be along the north pole of this magnet. To do that, hit F from your keyboard. You could see this select option, it will change from object to face. Just see here, I am hitting F from my keyboard. It has changed to face. Now zoom in, click on the magnet. So the face of the magnet is selected. Okay. Go to modeler, coordinate system, create faces. Snip on the selected permanent magnet. You can see a triangular snipping, that is the midpoint. Click here, go to the other surface, again triangular snipping, click here. So a new coordinate system has been created. You can see it under the coordinate system tab. If you expand it, see one new facies one is created. Now again select global. So global means our global working coordinate system. So after creating the facies, that is shown here as facies 1, click on global coordinate system, that is our working coordinate system. Now we have to assign this particular facies 1 to this permanent magnet. So click here, that is the permanent magnet. Now in the property window, you can see orientation is global. We have to change it to facies 1. So a small coordinate system, small axis you can find on the PM, that is the permanent magnet. Okay. Now we have to duplicate this permanent magnet and we duplicate this permanent magnet to create the south pole. That should be one pole pitch away anticlockwise from this from its position. So to do that, select it. Ensure that this selection is now object, it is not face. If it is face in your case, like this, hit object, like hit O from your keyboard, it will become object. So select the permanent magnet, duplicate around axis, click here, duplicate around axis. Yes. So one pole, we have to shift it by one pole pitch, that is 2 into pi by p. Okay. Make sure you are writing this angle in radian. That is by default, while you are writing an expression in ANSYS, particularly angle, you should write in radian. That's why 2 pi by p. Total number of magnets is 2. Hit OK. So a second magnet is created. Okay. Interestingly, you can see the orientation that has also been copied. Okay. That has also been copied. Now you can do two things. you can create a new facies. That is, you can create a new facies where this x-axis, it is directing outward now. You can create a new facies where the x-axis would be directed inward. To define this particular, that is the second magnet, as the south magnet, you can do another thing. That is what I am going to do now. So the second magnet, the name is PM1, PM underscore 1. Select it, go to property window, click on materials, scroll up, edit. So whatever the material is selected, click on clone materials. So new material is created. First change the name. I am doing it underscore capital S. Okay. Change the x component to -1. Now the north pole will be directed along the minus x axis of that particular coordinate system which is assigned to that magnet. Okay. Hit OK. Hit OK. See, the PM underscore 1 is now assigned to our new material, that is underscore S. Therefore, although the x-axis here for the PM underscore 1 is directed outward, as the working north pole is along the minus x-axis, therefore the whole magnet, this PM1, is become a south magnet. Okay. Now select both the PM, press Ctrl, PM1, hit on around axis. Now this set will be repeated by 90 degree, that is 2 times the pole pitch. So just multiply by 2. 2 into 2 pi by p. 2 into 2 pi by p. Total number would be half of the total magnet number, that is 4. Hit OK. See, all magnets are created. And you can see there are 4 north magnets, there are 4 south magnets. Okay. And if you click individually to all the magnets, you can see they are alternating. So all the north are alternating and has respective coordinate systems, different coordinate systems. South is like that also, alternating and has respective coordinate system. And automatically there are 8 phase coordinate systems as automatically created. Okay. So the magnet, stator, rotor are created. Now, if you can see, there are 36 number of slots and 8 number of poles. So if you do the HCF of 36 and 8, it would be 4. Therefore, this motor has a symmetry of 4. Okay. So if we can simulate only 1/4 of this particular model, it would be sufficient to grab the results. So we will reduce this model. For that, hit Ctrl A. So all are selected. Okay. First you have to ensure that your working coordinate system is global. Click on global. Now Ctrl A. Go to split. Hit split here. Now you can see the split is split using plane. That means XY plane, YZ plane, ZX plane, like that. Now we are splitting now here using YZ plane. And you can see one arrow is along the Z axis. Therefore, it will split by YZ plane and it will keep the right hand part and delete the left hand part. Okay. Here it is positive side, means along the arrow. It will keep positive side. And after splitting, split all selected objects and this box is checked that delete invalid objects. Therefore, the left hand part will be deleted. Hit OK. Only right part is there. Similarly, we need only the upper part. Again split. Now change the split plane to ZX. See, the arrow is now above. So we need positive side, that is the upper part. We want to delete the lower part. The box is checked. Hit OK. So the part at the first quadrant is kept and it is required. Hit fit all. Okay. Now we will create the coils in the stator. Go to draw, user defined primitive, RMX part, then lap coil. Put the dimensions same as stator dimension because the winding is in stator. Dia gap is D, dia yoke is DO, length is 0, no skew, slot is QS, slot type is 2, HS0 is HS0, HS1, HS2, BS0, BS1, BS2, and yes, layers is 2 because it is a 2-layer distributed winding. Coil pitch is 4. Now you can put anything greater than 1. If you put 1, it will be a concentrated winding. We need a distributed one. So the layers will be upper lower kind of, not side by side. So therefore any number greater than 1 would be enough. This end extension, all these things for 2D simulation, keep it 0. Seg angle is 0. Lane region is also 0. And hit OK. So see, the coils are created. Now do the same thing, the split operation again. Okay. You can do it beforehand. You could do it. We could do it beforehand also, that after creating the coil, we could split. But doing it again, it will help us memorizing. Split. So ZX. So the above part will be kept. Okay. Again split. Change it to YZ. So the right hand part will be kept. Okay. Fit all. Okay. Now this is the lap coil. Change the material to copper. Go to material, then scroll up, edit. Right here, copper. This is the copper. Hit OK. So it is under copper. Now we have to, if we select here lap coil, see the whole, all the lap coils are getting selected. We have to split it. For this, click on lap coil 1, that is the created object. Right click, edit, boolean, separate bodies. Now you can see this many lap coils, that is 18 lap coils are created. So go here, click on sheets, right click, collapse all, again expand. So these are all the materials. If you expand any materials, you can find all the objects under that material. Okay. Okay. In the meantime, hit save. It is a very good practice. So we have already created the coils, as you see here. Now we have to assign the coils, and before that we have to group them into various phases. Now this is a 36 slot 8 pole double layer distributed winding configuration. So you can use the winding function theory, or yes, this kind of things to understand that what would be the winding configuration. Also, we have told you in the class, Sir has told to use coil software to understand or to get to know what would be the winding configuration as per your desired um, harmonic level, as per your desired fundamental winding factor. So now uh, I know that uh, I I know that what would be the winding configuration for this thing. That's why what I am doing first, I am selecting the A phases. These six will be A phase. So after selecting this, in the properties window, I have to rename it. So I will write A, enter. You see all the objects are renamed with A. And after that, B, A minus C, this would be B, and it will be minus A plus C, this should be again B. Okay, it would renaming as B. And whatever the rest, if I select those, yes, this would be C. Now, for the ease of understanding, we may color it also as RYB. So this is our winding configuration. Now uh, we have to know that what are the positive terminals and what are the negative terminals. So these A terminals are positive, then it is minus C, then it would be plus B, then minus A, then plus C. So I know the winding configuration, that's why I am selecting it like this. So you have to know that what will be your winding configuration as per your requirement, as per your slot pole combination, and accordingly you have to select it. So I have selected all the positive sections of the winding, positive terminals. After that, I have to right click here, then assign excitation, then coil. So we should not change the base name. Number of conductors, it will be the number of coil terminals in half of the slot. So I am naming it as TC. So these are orientation or polarity would be positive. Press OK. Yes, it will ask what is TC. Suppose for this timing it is 1 I am giving. OK. Then we have to select the negative ones as well. These are negative. This is minus C, then plus B, minus A plus C, then it will be minus B. So these are all the negative terminals. Similarly, right click, assign excitation, coil. Don't change the base name. Number of conductors is again TC. Now this time polarity will be negative. Press OK. Okay, so if we expand the excitation, we can see all the coils we have assigned just now here in this list. Now we have to make the windings. Click on excitations, right click, add winding, change the name to phase A. It type should be stranded. Okay. Then the phase A here is created. Right click, add coils, select all A's. Okay. Now if you click on phase A, the phase A terminals will be highlighted here. Similarly, click on excitation, right click, add winding, change the name to phase B, stranded. Okay. Right click on phase B, add coils, select all B terminals. Okay. Right click on excitation, add winding, change name to phase C, stranded, okay. Right click on phase C, add coils, all the C terminals, okay. So the windings are made. Now we have to define that which part of this machine will rotate. Obviously the rotor part, but to define that we have to um, make a band. To do that, I will draw a straight line. This is the draw line option. Click here, snip on the center point like this. Click on any point on x-axis, right click, done. So one new line is there. Expand the create polyline, double click on create line. Point 1 would be 0, 0, 0. Point 2 would be D by 2. That means our bore radius minus LG. That means the air gap. Therefore, it is the outer radius of the rotor. Now, plus 0.15 millimeter. Okay. Hit OK. Select polyline 1. Then this one. This is sweep around axis. Click here. Angle of sweep will be 90 degree. Draft type natural. Click OK. So this is our outer radius of the rotor. Just outside that, we made a circular region. That means the circular region, which we are calling as band, it should include the whole rotor. Now rename this polyline 1 to band. And now we have to assign band. First, my recommendation would be make it transparent. Transparency should be 1. Okay. Now right click on the band, assign band. It is a rotation, like the movement is rotary. So click on rotation. Rotation axis is global Z. Data, right here, alignment, ALIGNMENT. This initial position is what would be the like uh, with respect to the drawing here, what would be the initial position of the band? That means what would be the initial position of the rotor? I will discuss it later, but for this time being, right here alignment is a new variable. Click on mechanical. It will ask you what is the alignment angle. Initial value is 0. Just click OK. Now mechanical angular velocity, right here NS is a synchronous speed. Okay. Yes, angular speed RPM. Now it is 1500 RPM. Okay. So band is created. If you expand under model, there is motion setup. If you click here, see the band is highlighted. Okay. And this part is moving. So now we have to create the boundary. So first thing to create the boundary, we have to again create a similar object as a circular object. We will now create that object in a different way. We will create a circle just to explore what all the things, what all way we can draw various things. Snip and click on the center. Expand it, click on any point on x-axis. Okay, so one new circle is being created. Double click on create circle. Center position would be 0, 0, 0. Radius would be DO by 2, that means it is the outer radius plus plus 1 millimeter. Okay, so it should include the whole geometry of the machine. Now we have to speed it the same way we have done before. It is along YZ plane, so therefore it will be the right hand side. Okay, we have to now take the uh, upper side, again split. This should be ZX plane. Hit OK. So we got our desired portion. Rename the circle to region, REGION. It's region. Enter. Similar to the band, change the transparency to 1. Okay. Now, as it is a part model, we have to define that this is not a complete part and it has continuity below the x-axis and on the left hand side also of the y-axis. To do that, we have to first understand that what is the type of this continuity. Okay, so we'll see it. First, you have to click or you have to press E from your keyboard. You can see here the selection will be changed from object to edge. Okay. Now you have to select this edge of region. It will show that region edge. Click here, right click, assign boundary, matching, independent. You click here, it will be independent, and you can see the arrow is outward. Keep it like this. Okay. Similarly, on the y-axis, zoom in, select this region edge, click here, right click, assign boundary, matching, dependent. Now you can see there is no arrowhead. That means the arrowhead is on the other side. Okay. So this boundary name is dependent. So it should have some independent boundary, that is independent one that we have just created now. First click here, make it reverse direction U vector. So these two, the two arrows of independent and dependent all are pointing outward. For this case, B dependent will be B independent. Why it is so? I'll tell you right. Tell you right now. So just for this time being, B dependent equals B independent. Click OK. Now why it is so? Because you can see here on this geometry there are two magnets. So whatever the situation of flux lines here, the same should be here. Suppose the GCD or the HCF of the slot number of slot and number of poles are odd. Here in this case, it is uh, like 4. So 1/4 model we have taken, and this 1/4 model there are two poles. Suppose in such some cases, if it is 8, so 1/8 model we have to take, and in that case, it may happen that in that reduced model only one magnet is there. So our portion will be like this, only this portion. So if it is so, if it includes only one magnet, therefore the direction of flux line here would be just opposite to the direction of flux line here. So the direction of B here would be just opposite of the direction of flux line here. If it is two magnets, or in better way, if it is even number of magnets are there, or even number of poles, rotor poles are there in the reduced model. So whatever be the uh, direction or polarity of B along the independent axis would be the same along the dependent axis. If the number of poles in the reduced model are odd number, then the direction of or polarity of B on the independent axis would be just the opposite of the dependent axis. Therefore, in those cases, B independent will be minus B of dependent while configuring the dependent boundary. Okay. Another vector potential, we have another boundary you have to assign. For that, click on this region edge, right click, assign boundary. This should be vector potential 0. Okay. Now the reason behind it, that here uh, this this one, okay, I have just changed the selection to object by pressing O. Here, this is the stator. It is a ferromagnetic material. So whatever flux is flowing through it, it should be confined to it. It will not spill out. It should not spill out. Now, suppose in a case, in a scenario of any electromagnetic device, you can understand that yes, uh, the flux may go out. So you have to assign this boundary accordingly. As I know that the flux will not spill out, I have made the region, that is the boundary, so close of the my original geometry. If it happens in some cases, some electromagnetic device, it may not be a motor, that flux may go outside the geometry in a large way. So you have to create this region large enough to accommodate all the flux. This vector potential 0 at this edge means that at this like beyond this edge there is not any flux from this system. So actually this is the infinite. We are defining it like this. This is the boundary condition. Okay. So boundaries are created, models are created, excitation are there. Now we have to make the analysis setup. Click on analysis, right click, add solution setup. Okay. So this is a 8-pole machine, and the speed is 1500 RPM. So 1500 multiplied by 8 by 120 would be the frequency. That means 100 Hertz. So we'll our stop time. For the first thing, we will. It is recommended to analyze for at least 2 cycles, 2 electrical cycles. So if it is 100 Hertz, one cycle is 0.01 second. So in this case, we'll put the stop time as 0.02 second. Change the unit to second. And it is recommended to uh, put the time step as 50 step per cycle. So one cycle is 0.01 second. So time step would be 0.01 by 50, that is 0.0002. But to get the idea for a very first simulation, you may reduce it to by 30 also. But for this timing, I'm making it by 50. So it is 0.01 by 50. It should be second. Okay. Save fields. To see the field flux line, for this timing, I am making it every step, not from 0 second, but from 0.01 second. That is after the first cycle, it will calculate the field. Okay. And you can do it from 0 also, as per your choice. And then after that, go to solver, nonlinear residual. I usually make it like this, 1 e to the power minus 6. And its general transient, all things are there. It's backward Euler. Nothing to change further. Click OK. Okay, now go to Maxwell 2D and design settings. Symmetry multiplier would be 4. So we are simulating a reduced symmetry, that is 1 by 4. So symmetry multiplier will be 4. In model settings, model depth, that means the stack length you have to define here. I am putting here as L. Okay. Now it is asking me what is L. The L may be 50 millimeter for our case. Change the unit to millimeter. Yeah. So L is 50 millimeter. Okay. And there is one more thing, that is matrix computation. It should be enabled, and apparent should be selected. It is required for inductance calculation. Press OK. All things are done. Now we have to check hit Maxwell 2D validation check. Yes, there are two things are there which are which warning is given. If it is error, there will be red cross. If it is all okay, green tick will be there. Exclamation sign means some warnings are there. Okay. So first warning is due to okay, we will remove the first warning, which is the boundaries. First thing is just we have to check one thing. Click on either stator or rotor. Under property, go to material, edit. View or edit materials. Yes, we can see here we have already assigned lamination 0.5, 0.95 stacking factor, and yes, these core loss model is electrical steel, KH, KC, KE, KTC, all values are there. So nothing to do with the material. Then what we have to do, click on any object, right click, assign excitation, set core loss. Now we have to set core loss for all laminated materials, that is stator and rotor. Hit OK. And we have to assign ADFX for all solid materials, that is permanent magnets. Right click, assign excitation, set ADFX. Okay, SPM and PM1. Okay. Now if you go to Maxwell 2D and validation check, see only one, and this is setup. This exclamation sign is there. If you assign some mesh on the objects, it will also go. But um, first, let us see what will happen if there is no mesh is assigned. That means there is a by default that automatically some mesh will be assigned by the software. We'll accept that and go for this tutorial. So first, we need to save this. Uh, then we should go to Maxwell 2D, analyze all. So you can see this progress is being shown. Click on the progress, you can see the progress. Okay. So as you can understand that there is no excitation, stator excitation is assigned, so it is a no load simulation. Click on result, right click, create transient report, rectangular plot, the torque. So move torque under this, that moving on torque, new report. So this is the average value, you can see that is 0, or you can click here, right click, trace characteristics, favorite, average. You can see it is almost 0, and the yeah, it's almost 0. So it is actually cognitor. In result, right click, create transient report, rectangular plot, winding, induce voltage phase A, phase B, phase C, new report. So you can see this is the phase induced EMF. So always you have to after designing or after modeling a motor in ANSYS Maxwell, always what you have to do, you have to see the induced EMF of the three phases, whether they are balanced, whether all the things are correct as per your expectation. Uh, So RMS. See, RMS values are almost same. So yes, this is perfectly okay. If you can find that there is asymmetry, so if there is no half-wave symmetry, there is some problem. Okay, in a symmetric machine, there should be a half-wave symmetry. Okay, now we can plot the field also at no load field. So Control A, right click, fields, the MAC okay, all objects, uncheck full model, done. Okay, now yes, this is the 10 millisecond. From 10 millisecond only, we have started our field calculation. It's 10 millisecond, okay. Now under field overlays, expand this, double click here. So you can see the field. Okay. So at 10 millisecond, actually it is only like moved here. The rotor is moved here. Okay. So that's why it is showing like this. Okay. Now again to see the um, flux lines, Control A, right click, field A, flux lines, all objects, uncheck full model, done. So B means flux density, A means flux lines. Double click on this scale on of A, change rainbow to magenta, close. So flux lines are more visible. Now, yes, it is getting some weird that the rotor is here. If there could be a continuation, that it could be better appreciated. For that thing, nothing you have to do. Just expand the analysis. Double click on setup one. Under save fields, every one step from 0 second to 0.02, you can make it. Okay. Now come here, click on result, right click, clean up solutions, do deletions. Then again, simulate it, analyze, Maxwell 2D analyze all. So it will again simulate, just simulating. Now double click on time equal to -1 here, at 0 second, click on OK. So you can see the fields are here. So these are no load field. Okay, first save it. So you can see the flux lines are also symmetric. If you see there is any discrepancy, so that flux lines are not symmetric at no load. For a symmetric machine, there should be some, there are some problem. You have to address that. Now, what I told you earlier, that what is this alignment angle? We need to clarify it. So, firstly, the alignment angle is nothing but the initial rotor position. That means at time t equal to 0, what would be the position of the rotor? Okay. So, at the starting of the simulation, whether this, if alignment angle is 0, this what you are seeing on the screen, this would be the rotor position. If I want the rotor position to be changed at time t equal to 0, what it would be, that we have to define by putting the value of alignment. Now to understand that, just see this figure. Okay. So while assigning the phase terminals, we have assigned these three terminals as as positive A, and these three red terminals as negative A. So if it is positive A, it means that the current is coming out of the screen. That means if this is x-axis, this is y-axis, z-axis would be out of the screen. So current from these terminals are coming out of the screen, and for this terminal, the phase current is going inward the screen. So the flux due to this red, that means A phase coil, would be like this. Like this would be the vector. So here, this is the midway. This is the mid path of this coil. The resultant flux would be inward like this. Okay. So, okay, this is first thing. So we can so we can say that this is as A phase axis. And while defining this magnet, we defined the magnet orientation to be outward. Okay. So you can say the magnet axis for this magnet is this blue line. Okay. Now, if uh, we consider the direction of phase axis as positive, then this blue direction or the blue line would define the negative d axis. Okay, as it is outward. Now come to this picture. We know from the phasor diagram that along the d axis, uh, we have to along the d axis the permanent magnetic flux will be there, and we have to place the current phase current to the q axis to get the maximum torque, as the torque is stator flux multiplied by rotor flux into sine delta. The delta is the angle between stator flux and rotor flux. If it is 90 degree, the torque will be maximum, considering there is no reluctance torque. Because completely the reaction torque. Now, therefore, we have to, if the magnet is along d axis, we have to align the current with q axis. Okay. Now, if this is minus d axis, the q axis is 90 degree behind it. So this line is q axis. Okay. Therefore, this line is q axis. Therefore, if I excite the A phase with cos function, with cos current, if I excite the A phase with cos current, then I have to align the rotor, this axis, like this is the q axis of the rotor, this axis with this red axis. I have done a small mistake. The direction will be like this. Yeah. So we have to align this black arrow with the red arrow to get the maximum torque. Given the uh, winding is excited with a cos current, then at time t equal to 0, maximum value of phase current we will get. But now, if I excite the A phase axis with a sine component, therefore it is already lagged by 90 degree. To compensate that, now we have to align the A phase axis with minus D axis. Previously, what was there? Previously, current was like this. So maximum was here. Okay. Maximum was here. So it is aligned with Q axis. Now what is happening? Minimum is here. That is the zero crossing is here. So therefore the maximum is occurring here along the D axis. Now if I want this maximum to be here, then I have to align the A phase axis to minus D axis. Just I have to rotate anti-clockwise. Then this maximum will come here in case of sine excitation. Now, where is the minus D axis? This blue line is the minus D axis. Now, if I align this blue line to the red line and assign sine excitation in the stator, sine current in the stator, my job will be done. So, the angle here, this angle is 30 degree. 10, 20, 30 degree, and this is 22.5 degree. Here it is 45 degree, it is 22.5 degree. So the difference here is 7.5 degree. Okay, 7.5 degree. Now our alignment angle would be 7.5 degree anti-clockwise. That means positive 7.5 degree. So the job of this alignment angle is to align the A phase axis and Q axis. That is to ensure that if there is no reluctance torque, only reaction torque is there, the rotor position should be such that maximum torque will occur. So we'll now come here in motion setup. Oh, sorry, we'll just click here, and in alignment we'll write 7.5 degree. Done. Now, in addition to that, we'll now in excitation, here we have to remember we have to assign sign excitation. So it should be RMS value of phase current, suppose it is IPH, multiplied by SQRT, square root of 2. That means the peak value of RMS current into sine 2 into pi into F. What is F? That is 100 Hertz into time sine 2 pi ft. Okay, copy this thing, Control C, hit OK. It will ask you what is the current, change the unit to ampere, suppose it is 10 ampere. Okay, go to phase B, paste the expression. It would be 2 pi ft minus 2 into pi by 3. Okay, hit OK. Phase C, Control V, it would be plus 2 into pi by 3. Okay, done. Okay, so the excitations are there. Now save it first. Maxwell 2D first validation check. Fine. Maxwell 2D analyzer. Okay. Now click on torque. So I see this, there is an average value of 6 Newton meter. Okay, so this is the torque is generated. This is the um, terminal voltage. Okay, you can see there is a small there is no half-wave symmetry, there's a small asymmetry. If you zoom here, you see this is the midpoint, isn't it? This is the midpoint. Just slight asymmetry is there. As this is SPM, surface permanent magnet machine, so the asymmetry which results from the armature reaction will not be that much visible, but yes, you can see that there is very small asymmetry. You can see the same thing in the flux also. Double click on time 0. Okay, now you can see that at 0 time it is 7.5 degree ahead, so it is visible here. It's the flux density. This is the flux line. Could you see there is some asymmetry? This is not completely symmetric like before, so it is on load. This defines that it is on load. Okay, so this is how you can simulate a motor. We're almost done. Just we'll plot some more things. Create transient report, rectangular plot. There can be under winding, there can be inductances. So phase A, phase A, phase B, phase A, phase C, phase A. So Yes, these are the inductances. There can be loss, core loss, eddy current loss. Core loss are the addition of excess hysteresis, these losses. So just core loss, eddy current loss, and sorry, core loss and solid loss will be sufficient. This eddy excess and hysteresis is the summation of those are the core loss. So core loss and solid loss. Uh, this core loss is combined of stator and rotor, and solid loss is the magnet loss. Okay. So you can see there is a transient thing. So what I do, I just take the average of last two cycle. So right click here, right click, trace characteristics, click on all. Then yes, click on average. Then in the range, it should not be full. It should be specified. Now it is 20 millisecond. You can take 10 millisecond also. So the last electrical cycle you are taking. You can see, yes, after the midpoint, after 10 millisecond, it is steady. So 10 millisecond, add trace characteristics, close. So this is in watt, 99 watt, around 100 watt is the core loss, and 1.3 watt is magnet loss. Okay, so other another one important thing that I would like to tell you. For that thing, just close the visibility of the plot. Okay, that is a very important thing, that is magnetic loading, that is air gap flux density waveform. For that thing, you have to create an arc. So select a center point arc, snip on the origin. Okay, click on a point, any point on x-axis. Okay, then snip on any point on the y-axis, like this. It has to be on the y-axis. 1 minute. Right click, done. Okay, so there is a new polyline. Expand the create polyline, double click on center point arc, create angular arc. So the start point is 47.8, make it user defined. That is d by 2, d by 2 minus lg. You can make it okay. So we'll compute the average, compute the air gap flux density at the middle of the air gap. So d by 2 minus lg by 2. Okay. Okay. So you can see this line is just at middle of the air gap. This is the line. Okay. So rename this polyline. Click here under property window in name AG air gap underscore air gap art. Press enter. Okay. Fit all. Okay. Go to Maxwell 2D, then fields, then calculator. Okay. Now here under quantity select B. Okay. So under vector scalar, then scalar x. So we are taking bx, b along, like b along x-axis, x component of b. Then function phi. Okay. Then under scalar, under trigonometry, select cos. So it is cos phi, multiply here under general star. Okay. So it is bx cos phi. Then again quantity b, here vector scalar, scalar y, function phi. Okay. Trigonometry sine. multiplication, addition. So we actually created the radial component of B, that is Bx cos phi plus By sin phi. Okay, click here, add, name as B rad, is B radial. Okay, okay, done, done. Okay, then go to result here, click on result, right click, create fields report, rectangular plot. In the geometry, select AG Earth. Okay, now you can see here is our defined this expression is B rad. Okay, uh, uncheck this default under X, then click on these three dots, and it is, I would recommend to do it, uh, 1 second. Yes, normalize. Okay, normalize means the distance would be from 0 to 1, like it. Okay, now new report. So this is the average area flux density, and we have already loaded it, so it is on load. So trace characteristics, favorites. If you put average, it would be 0. So make it absolute average. 0.72 is the average air gap flux density at load. So it is not the magnetic loading. Magnetic loading is when it is or at no load. So you just double click here, make the IPH, it is 10 ampere, make it 0 ampere, enter, run the simulation again. Okay. So whatever be the calculator expressions plot, that is the B rad, if you double click here, if you double click here, this is 0.719. So this is the no load air gap flux density. The average value of it is the magnetic loading. So this is all the things for uh, basic uh, design or how to model a motor in ANSYS Maxwell. One more important thing is there. We can do one thing. I will not go in detail of that, but yes, I will say something about it. See, in this phasor diagram, if you see, we will place the phase axis along the q axis to get the maximum reaction torque. Suppose it is a IPM, so it has reluctance torque along with reaction torque. So when the torque will be maximum for what internal power factor angle, the torque will be maximum. If that we have to determine. So this is the suppose this is the current vector, and this is the angle, that is gamma, internal power factor angle. So where the torque would be maximum. To determine that, you can do one thing. For each phase, you can add one angle plus GA gamma. Okay. And now we have to define what is gamma. Unit type angle, and unit is degree, it is fine. First make it 0. Okay. Phase B here also plus GA gamma. Okay. Phase C also plus GA gamma. Okay. So now to determine that where at which angle, suppose I have aligned, so with the alignment angle we have already aligned the q axis with fs axis, and now at what internal power factor angle I will get the maximum torque. To do that, click on optometrics, right click, add parametric, here add So the variable would be gamma. Now start simulation from 0 degree. If it is IPM and you know at the second quadrant the peak of the torque will appear, then start from 0 degree to 90 degree. You can get a take a step of 10 degree. Further, you can refine also. Add. Okay. So at the table, there are total 10 simulations. Hit OK. Expand the optometrics. Click on parametric setup 1. Right click. Analyze. So it will start analyzing all the 10 simulations you can see here. So I forgot to mention one thing that when you start analyzing this parametric setup, you should turn the shape fields off. It is click here none, then hit OK, because it will take longer if it at every step you need to calculate field. So yes, it took a long time, and we skip that. I skipped that time. So how could you know what would be the optimal angle? Click on result, right click, create transient report, rectangular plot. So it is already torque, moving on torque. Write AVG average, one first bracket will be at the end of the expression. So it will be average of moving on torque. Primary sweep, it is not D, go to families. Gamma head is nominal, click on these these three dots, then use all values. So it is gamma all now. Now go to trace, primary sweep, change it to gamma. Okay, so it will plot. So it will plot the average torque against gamma. Okay, new as it is a surface power kind of machine. We are seeing that at 0 degree, that is where the F is current, peak of F is current, or you can say yes, the F is axis is aligned with Q axis, that is gamma equal to 0 degree, the torque is maximum. Okay, but you can see that the state is here 10 degrees. And so as we can understand that yes, the peak is at 0 degree, you can further refine it by doing from 0 to 10 degree with 1 degree step. Okay, so suppose for IPM, for a machine which has a reluctance torque along with reaction torque, suppose at 20 degree you can find the uh, uh, peak of torque is happening, then from 10 degree to 30 degree you can again do the same job with some uh, very fine stepping, maybe 1 degree. Okay, so in that way you can get the optimal gamma. So it is all about simulating a permanent equation or a synchronous motion, as I say, in ANSYS Maxwell. Thank you very much.